This is part 3 of lecture 1, and in the previous part we have done the interesting part, the examples, and now we need to move on to doing the mathematics, which is the boring part, but you need it for the homework and for the exams, so let's do this. So in the previous part we stated the problem that we try to solve, the classification problem. So suppose we get images of, say, cats and dogs. So these are, say, cats, and these are dogs, and you use two features to represent them. We use them as the input, and for example, x1 could be the height and x2 could be the length or width or whatever it's called, and we want to find a function that maps these two features to a label y hat, which is either cat or dog. So we'll call cats 0 and we'll call dogs 1. So we need a mathematical function that, given a pair, given a value x1 and x2, we need to figure out whether it should be labeled 1 or 0. So for example, this one here should probably be labeled 1, and if you have a point in the middle, then it's not really clear, but we want to make the best guess. So for a problem like this, it seems the simplest version of a function is a linear function, a linear classifier. So it's a line. Use a line, and things above the line will be classified as 0. Things below the line will be classified as 1. So that seems to be the problem, and we want to find such a line. So finding a line seems difficult, but one thing that we need to do first is how we're going to represent this line. So how can we relate a line to a function that inputs two values and output either 0 or 1? So that's the first problem we need to figure out, and then we can figure out how we're going to find this particular line that separates the two classes. So let's focus on the first one. So in 2D, it's kind of obvious what we should do is we can write down the equation of a line, and then when it's above 0 and when it's below 0, we can classify, return, 0 and 1. But it's not very clear how to do it in higher dimensions, because usually we have more than 2 dimensions. So for example, if we want to use images, we want to use pixel intensities, then there is a huge number of pixels in each image. So the number of these things will be huge. So we need to consistently write these down. And what does a line mean in higher dimension is not very clear. So let's start with one-dimensional and then move on to 2 and then 3, and then hopefully we can generalize that way. So let's start with 1. So suppose there's only one feature, x1, say height, and cats are smaller and dogs are larger on average. And one way to get a classifier is to just use a threshold. So a threshold can be written as when x1 is larger than or equal to a, I would output 0, and when x1 is less than a, I would output 1. That would be an example. Actually, for this one, it's reversed. So let's do smaller or equal and larger. Next, moving on to 2D. As I said, we can write down the equation of a line. So when x2 is larger than or equal to, so larger is above, say mx1 plus b, so the slope plus the intercept. When this happens, we will classify it as 0, and otherwise we will classify it as 1. So that is somewhat problematic, not always, but when the line is a horizontal line or vertical line, it's not very clear how to write these things. So we will wait. When we see the 3D, let's draw something 3D. I'll just randomly label the axis. We're not doing computer graphics, so it doesn't matter. And so I'll do x1 to 3 this way, and the cats are these, and the dogs are, say, these. And we want a line. A line cannot separate anything, so we need a plane. So maybe a plane like this. Hopefully it's clear. what the plane looks like. So the plane is like a almost horizontal plane that cuts through the x3 axis. How do we write the equation of a plane? So there are many ways. The parametric way probably won't work. So the normal form could work. So for those of you who have not seen this, I will talk about this. I'll explain more about this in homework 1 video. So I'll record another video to go through homework 1, and in that I'll talk about normal of a plane and some kind of algebraic geometry stuff. So assuming you know the way to represent a plane, it's ax1 plus bx2 plus cx3 plus d, whether it's larger or smaller than 0. So say when it's larger, we'll classify it as 0. When it's smaller, we'll classify it as 1. So these three looks different. So it looks like it's kind of hard to generalize, but the three-dimensional version looks very clean, and it seems we can write these two the same way. So indeed, this is what people normally use. We use an expression like this, and we call the coefficients the weights. So we'll write this one as w1 x1 plus w2 x2 plus w3 x3 plus b. We will use this expression, whether it's larger or it's smaller than 0, to represent a high-dimensional plane. So if you have 4 or higher dimensions, you just add the terms w4, x4, and so on. So note that we can do the same thing here. So this is just mx1 minus x2 plus b, whether or not it's larger than or equal to 0. So basically m is w1 and minus 1 is w2, and b is the same. So similarly here, it's just a minus x, whether it's larger or smaller than 0. So we can rearrange it. So w1 x1 plus, let's call ab anyways. So whether this is larger than or 0 would determine whether you are in class 1 or 0. So okay, so now we have a form to represent this function. And we don't always want to say when something's larger, I will label 0. When something is smaller, I will label 1. We'll use a simple mathematical notation, the indicator function. So in the next slide here, we will have this expression here. So the thing inside is just the expression of the hyperplane. So this is in the n-dimensional space. M is usually the number of features. And this is representing a n-dimensional hyperplane. So basically like a line or plane in m dimensions. And the indicator, as I talked about, is a mathematical function. I usually write this as an open 1. And it basically says if this thing here is true, then it's 1. If it's false, then it's 0. So basically when this is indeed larger than 0, this function returns 1, and otherwise it returns 0. So also, because we are always dealing with very high dimensional spaces, we want to use vector notation. So instead of writing the dot 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 stuff every time, so we will use the notation x transpose w or w transpose x. They're actually the same. So w here would be the vector w1, w2 until wn. So w transpose is just the horizontal version of this. So if you write w transpose x plus b is basically this vector, or it's actually a matrix multiplied by the x vector plus b. So when you do matrix multiplication, you do a row multiplied by a column. I mean, the row dot product a column, and add the b. So it's w1 x1 plus w2 x2 plus so on plus w mxm plus b, which is exactly the thing we had. And we also have a very fancy name, by the way, of this very simple linear classifier. It's called the linear threshold unit perceptron. So I usually call it the LTU perceptron. So it's called a perceptron because later it will become a part of a neural network. So in the next week, we'll talk about network, and then you'll see why we are calling these things perceptrons. So again, they are part of a neural network. So it's a basically one unit in the network. So as I said, these things are called weights, and the B is still B because it represents bias. So weights and bias. So sometimes I'm calling all of these weights. So B is just a special weight. There's another terminology that's related to neural network is the activation function. So again, wait until next week to see why it's called the activation function. So an activation function is basically the function that maps whatever this linear combination is. So wx plus b, we want to map it to the prediction, so y hat. So y hat is some function of this, and we're calling this function the activation function. So in particular here, for the LTU perceptron, the activation function is just the indicator function. We talked about the equation of a line already, so I'll skip this slide. And we talk about the hyperplane thing. As I said, I will talk more about it in homework 1 video, so I will skip this as well. And now the important part. So we figure out how to represent a classifier or an LTU perceptron, and now we need to figure out how to get that line. So the problem now is, given the training set, so remember the training set is just a sample that we have that's already labeled. So x1 is the feature, y1 is the correct label, and similarly x2, y2. And by the way, they are called instances. So each element in the training set is called one instance. So here we have n instances, we have n number of data points basically, and the problem is to figure out what are the weights and what is the bias. And this process is called training. I think we talked about it before. And one algorithm to train this perceptron is called, well, obviously the perceptron algorithm. Let's first look at another very obvious way to train this, basically guess and check. So it's usually called the brute force method, and basically we have cats and dogs again. What we are doing is just we guess one, and then, well, it's making mistakes, so we guess another one, it's making more mistakes, so we keep guessing until somehow we're lucky and we get something that classifies everything correctly. So in 2D, that seems possibly reasonable. But imagine if you have like a 10,000 dimensional space and you are guessing a line, a hyperplane. It's kind of hard to get it right. And also, sometimes the structure of the data is not like this. The structure looks like this. So there is, among lots and lots of lines, there is actually only one that works. So these ones are hard to get. So brute force seems very time-consuming, so we are not going to use that. Actually, in most of supervised learning, we always want to try some kind of iterative method. So what I mean by iterative is we always start with something random. So start with a guess, for example, guess like this. And each time we try to improve this. So we want to go in a certain direction and we want to reduce the mistake here. So for example, if we start with this, maybe we look at this particular image and it's classified incorrectly. We want to somehow rotate this line and maybe you will classify this correctly. And in the process, maybe it's doing a better job at this particular point, but it's classifying something else incorrectly now. So, however, if we keep doing this, maybe, hopefully, at some point they will converge. They will slowly move, basically rotate and translating until you get the correct line. So that's the basic idea for the perceptron algorithm. So it's an iterative algorithm. We start with something random and we move every time. The goal of each move is to make it better. So to actually talk about the algorithm, it's random weights, and then we use the activation function. Basically, we use the random weights to predict one instance, so one sample data point, x, and we will get our prediction y hat. Note that it's an instance, so it's already labeled, so it's already in our sample. So we have xi, and we also have yi already. But this random weights, when it's activated, it can generate a prediction, and that prediction may not be the correct label. So we are dividing into two cases now. So the first case is it is actually correct. So yi is y hat I. In that case, just do nothing. So I'll write do nothing here. And the second case, there are two types of mistakes. And one is actually it's a dog, and you are classifying it as a cat. Or it's the other way. Actually, it's a cat, you are classifying it as a dog. So in the first case, we're going to increase the weights by x, and in the second case, we're going to decrease the weights by x. So these two seems very arbitrary, and it's not clear intuitively at all how can the weights be related to the x value, and why can we just add the weights to a data point? So that may seem kind of confusing. So I'll use a diagram to try to explain this geometrically. Hopefully it will become more intuitive. Let's do it in the next slide. So to make everything simpler, we will use the two-dimensional example, and also we'll assume the bias is 0. So we'll assume B is 0. So the line will be this. And in particular, if you write it in vector notation, it's just W transpose X is 0, which means they are orthogonal to each other. Let's have some points. So these are the cats, say, and let's also have some dogs here. And let's initially start with something that's almost right, and say this. So this is our random W, W1, W2. So let's first figure out how to actually represent this vector W1, W2. So as we see here, W transpose X is 0, so they are perpendicular to each other. So we will have a vector like this. So this will be the W vector. It's perpendicular to the line. So the direction of the vector should also face whichever direction is classifying stuff as 1. So this is the 1 side, this is the 0 side. So I will explain more about the normal of a plane again in the homework 1 video, so I will not talk a lot here. But basically, we can represent the vector W as something that's perpendicular to the line and also pointing towards the direction of the class 1. So this is our W here, and let's look at what we should do. So if there is something that's a 1 and it's actually classified as 0, let's find one like that. We should increase. Okay, which one is like that? So this is a 1, and we're classifying as 0 because this is on this side. This side is 0 side, and so we are classifying this point as yi is 1 and y hat I is 0. So we want to increase w by x. So what is x? X is just this vector. This is our xi vector. So increasing w by x, which just means w and then move by x. So our new w will be like this. This is our new w. So note that our new w is also perpendicular to the actual line. So if we draw a line, it will be something like this. So this is our new line. So now it seems it's not improving a lot, but at least it's classifying this one correctly now, because this side is 1, this side is 0. So this is a 1, and now it's classified as 1. So we are at least improving on this point. So we'll see later why we shouldn't update it by 1 times x, but we'll talk about this later. That seems to be working. Let's try the other one, which is one that's classified as 1 incorrectly. So this one is 0, and yi is 0, and y hat I is 1. So according to our algorithm, it's the second case. We want to decrease w. So this x is this vector here. And if we increase it, we go this direction. If we decrease it, we go the other direction. So if we go the other direction, then our new w again is going to be some vector like this, and the line that's perpendicular would be something like that. So that would mean this side is 1, that side will be 0. So again, this point is classified correctly, but again, it destroys other points. But at least the point that we are focusing on gets classified correctly. So this is the basic algorithm. We can repeat this for each point. And so for example, here, if we update to this new line, then we are classifying these things incorrectly now, and we can move the line again to basically rotate the line around until it reaches the point where it's kind of horizontal and classifies everything correctly. So let me formalize the algorithm, the complete algorithm. So the input is a bunch of training instances, and the output is we want to get the weights and the biases. There's no S. And we initialize the weights. We usually initialize them to something that's a random number between minus 1 and 1. So the uniform is just a notation for picking a random number between minus 1 and 1. And then we evaluate this activation A. Basically, we use the random weight to classify this xi point and get this ai. I used to call it y hat I. It's not a good notation, so I'll change it to ai here. And then we use the following update rule. So this is the mathematical update rule. And when alpha is 1, it's exactly the same as the description. So let me actually try this. So if ai is yi, or the notation we used is y hat I is yi, if they're both 0 or if they're both 1, then this term will be 0. So w is basically w. So nothing changes. So that's okay. If ai is 1 and yi is 0, so if a cat is classified as a dog, then this minus this is 1, and this whole thing, when alpha is 1, is w is just w minus x, the same expression as we had before. And similarly, b is, we didn't have b in the diagram, so let's talk about the other case. When ai is 1 and yi is 0, oh, sorry, I'm saying this wrong again. When AI is 0, when it is a dog and is classified incorrectly as a cat, then 0 minus 1, this is minus 1, so minus minus is plus, so W is updated to W plus XI, again, the same as our description before. So this expression basically captures the same idea of the 3 cases we had, so we will use this as the update rule. And we want to repeat this for every x and repeat this many, many times. Okay, so now note that there is this alpha here. So remember what we did in the previous diagram, when we update, we're updating too much. So I will actually move to the next slide and have the diagram that we had. So remember we had this, a bunch of training instances, and we update according to this one, and then we switch the lot and we classify many other things incorrectly because we are focusing on this point, focusing on classifying this particular thing correctly, and we move too much. So if we don't want to move too much, maybe we just want to move a little, maybe not even enough to get this one correct, but we want to move stuff slowly. We don't want to just randomly switch between 2 completely different lines. So if we want to make the switch smaller, we may want a learning rate alpha that's smaller than 1. So when alpha is 1, you saw it's the one we had. So when alpha is smaller than 1, it's learning slower than just update to fix each point. So for example, when alpha is 0.01, it may be too small, so one update is not enough, but you can update twice, right? So you can use the same point to update twice. So it can gradually move until it gets that point correct. So that's actually better than just jumping around randomly. So having a learning rate that's small would be helpful if we don't want to change everything too much. So that's why there is a learning rate, and the learning rate is multiplied by this x to make the change smaller every time. And when you are actually implementing this algorithm, you need to try different alphas and see, sometimes it's going too slow. So it takes too long to converge to anything. Sometimes it's just updating every time, so the number of mistakes is changing, like randomly changing every time, so you know that you should decrease the alpha. So you need to adjust the algorithm by changing alpha, basically. So for perceptual learning, it's actually typically set to 1, but we might want smaller changes so we can train a shorter number of iterations. And when we talk about support vector machines, we'll actually talk about having a learning rate that's not constant. Actually, when we do neural network, we will talk about that. So we could have learning rates that are changing. So at the beginning, it could be 1, and then later it would go slower and slower, and we can change it in other way as well, but we usually decrease every time, and at the end, when it converges, will not move, basically. And I will have a quiz question at the end, so that's lecture 1.